Hello, we are from Group 14. My name is Nathan, and these are my group members, Johnson and Adibah. Today, we are going to present our topic on material selection and sustainability. The product that we've chosen is the Olympic barbell. The Olympic barbell is a specialized equipment typically made from carbon steel that is designed for competitive weightlifting and general resistance training. It consists of a long steel bar with rotating sleeves on each end, which enables it to hold standardized Olympic weight plates. The bar typically measures 2.2 meters in length and weighs 20 kilograms for men's bar, while women's bar are slightly shorter, measuring at 2 meters and weigh 15 kilograms. The Olympic barbell was first used in the Olympic Games during the early 20th century. Over time, the barbell's design evolved from wood to include bearings and high tensile steel that allows it to withstand loads exceeding 700 kilograms and decrease the stress applied on athletes' wrists and elbows. The Olympic barbells can often be seen in competitive weightlifting competitions. Other than that, Olympic barbells can also be found in gyms and are often used for general strength training and conditioning. The Olympic barbells are often used in exercises like squats, deadlifts, and bench presses. Moving on, we'll talk about the key properties.
For the first key property will be tensile strength. Tensile strength is the maximum stress a material can withstand before it breaks. This is extremely important for Olympic barbells because athletes perform explosive lifts with very heavy weight. Most premium Olympic bars are designed to have tensile strength value between 1,400 to 2,000 megapascal. For example, Rocky Olympic barbell is around 1,310 megapascal, and Eagle's IWF certified bar reach 1,480 megapascal or more. A higher tensile strength means the bar is safer and less likely to snap. But if it becomes too high, the bar may become overly stiff or brittle. So the goal is to achieve a balanced value that ensure both safety and performance. The next one will be yield strength. Yield strength is the point where a material begins to bend permanently. Once it passes this limit, it cannot return to its original straight shape. For barbells, this is critical because repeated heavy lift can easily bend a low quality bar. High quality bars typically have a strength between 1,100 and 1,600 megapascal, while cheaper bars with only 900 megapascal tend to bend quickly. A high yield strength means the bar can flex during lift but still return to its original shape. This is what gives Olympic bars the unique combination of flexibility and durability.
Next, I will talk about the third and the fourth mechanical properties. The third mechanical properties is modulus of elasticity. Modulus of elasticity also represents the stiffness of a material. The modulus of elasticity shows how much an Olympic barbell bend under loads. A bar with the right modulus of elasticity can store and release the energy during lifts, helping lifters use the rebound to lift more efficiently. The modulus of elasticity of the bar also affects the snap and jack differently. Olympic lifters prefer bars with good elasticity for better performance, while power lifters use stiffer bars. Bars with very high modulus of elasticity are too stiff and not suitable for Olympic lifts because they reduce the beneficial flexibility of the bars. The fourth mechanical property is density. The Olympic barbell is constructed with a denser material. A denser material have a tighter atomic structure, making it more resistant to bending or breaking under heavy loads. Density affects the weight distribution of the bar. A uniform steel density allows the bar to spin evenly on both ends, ensuring smooth rotation of the sleeve during lifts. This balance helps lifters maintain control and reduce the risk of injury.
The peak strength is the maximum stress a material can withstand for a specific number of load cycles before it experiences permanent deformation or breakage. In the context of an Olympic barbell, users lift and drop the barbell repeatedly, sometimes with loads over several hundred kilograms. The bar undergoes tensile and compressive stresses at its outer surface. Over time, this cyclic stress can cause microcracks to form and grow, leading to fatigue failure.
AISI 4140 alloy steel. is the most ideal material for the Olympic barbell because it has the most balanced mechanical performance. First, it has very high strength. Tensile strength is around 1380 megapascal. Yet strength is around 1170 megapascal. This value means the bar can withstand extremely heavy load without breaking and won't permanently bend even after repeated use. Next, its modulus of elasticity is around 205 gigapascal, giving it the ideal stiffness. This is what provides the current wave during Olympic lift, helping athletes build momentum. The density of 7,850 kg allows the bar to meet the official weight requirement of 20 kg, while also ensuring perfect balance and stable rotation at the sleep. The ISI 4140 also has excellent fatigue resistance, meaning it can survive millions of lifting cycles and repeated drops without developing cracks. Overall, AISI 40 offers the best combination of strength, stiffness, durability, and safety, which is why it is widely used in the competition-grade barbell.
Next, I will talk about the silicon carbide composites. The tensile strength of silicon carbide composites is around 250 to 500 megapascal. The high tensile strength of silicon carbide composites means it can perform excellent resistance to fracture under heavy loads. The modulus of elasticity of silicon carbide composites is around 370 to 490 gigapascal. The density of silicon carbide composites is around 3.1 grams per centimeter, and the fatigue strength of silicon carbide composites is around 250 to 350 megapascal. It means the silicon carbide composites is cracked easily. One of the important points is that silicon carbide, like small ceramics, does not exceed a yield point. It fractures elastically when overloaded. Then, the silicon carbide composites also provide various types of advantages. First, silicon carbide has very high corrosion and oxidation resistance. It doesn't rust and maintains its properties even when exposed to aggressive chemical or oxidizing gases. Secondly, it has excellent wear resistance. Its ceramic nature gives it super hardness, meaning it resists scratchings, abrasions, and erosion effectively.
Another material class that was chosen is the carbon fiber reinforced polymer. The matrix is a biphenyl A epoxy and the fiber is Tori T700, which is a polyacrylonitrile based carbon fiber commonly used in sports. By combining these two components, the final composite carries the properties of both the epoxy and the Tori T700 fiber. This material provides a tensile strength between 2,500 and 3,000 megapascals. It does not have a yield strength because carbon fibers behave in a linear elastic manner and fracture directly. Its modulus of elasticity ranges from 155 to 165 gigapascals. The density is about 1,600 kilograms per meter cube, which is far lighter than the steel normally used for Olympic barbell, which is around 7,800 kilograms per meter cube. In terms of fatigue strength, the material does not have a clear fatigue limit. It slowly degrades over many cycles, although this can take millions or billions of cycles. The main advantage are that the material is much lighter than steel and it offers a higher specific strength. Out of the metal, ceramic composite, and carbon fiber reinforced polymer options, the best material for an Olympic barbell is AISI 4140 alloy steel. This material offers the most effective mechanical balance. It provides high tensile and yield strength with a modulus of elasticity of about 205 gigapascals. It also has strong fatigue resistance, which is important for repeated loading in lifting. Even though Tori T700 based carbon fiber reinforced polymer has greater mechanical properties, it can experience brittle failure. It does not give the ductile behavior needed for a safe barbell. AISI 4140 alloy steel can yield and deform when overloaded, which helps prevent sudden catastrophic failure. For these reasons, AISI 4140 alloy steel is the best and most reliable choice among the three material classes.
AISI 4040 is also a strong choice from a sustainability perspective. First, it is highly recyclable. Steel can be melted down and reused without losing its properties, which support a circular economy and reduce overall waste. Second, Using recycled steel reduces carbon emissions up to 60 to 70% compared to producing new steel from raw ore. This is significant because the steel industry is responsible for around 9% of global CO2 emissions. Next, AISI 4140 has a very long service life. Its durability means the barbell rarely needs replacement, which helps reduce material consumptions and lowers long-term costs for gyms and users. Finally, its material support the socio-economic side as well. The steel industry provides jobs in manufacturing, cutting, and recycling. At the end of its life, the barbell still retains economic value because it still can be recovered and reused.
In short, throughout today's discussions, our group have discussed three types of materials. The first material is AISI 4140 alloy steel, the second one is carbon fiber reinforced polymer, and the third one is silicon carbide ceramics. So in our final decisions, our group chose AISI 4140 alloy steel become the Olympic barbell materials. The reason is because it has high tensile strength, good fatigue resistance, ductile behaviors, and a suitable modulus of elasticity, which together provide both safety and performance. It is also cost-effective, durable in long-term use, and fully recyclable, helping to reduce carbon emissions. Therefore, we believe AISI 4140 is the most practical and sustainable material for this application. Thank you.